Swayam Prabha. Digital India. Educated India.
So welcome back everyone, and in this module we will begin our discussion on how to apply conservation, linear momentum conservation in the case of collision theory. We will begin our discussion with the case of two isolated particles and see what are the changes that the collision of two isolated particles brings in. Okay, so primarily our entire discussion is driven by conservation of linear momentum. So LM means linear momentum here, and we will start our discussion on isolated system of two particles. Okay, so the collision is we talk about collision when two particles, if two particles approach each other, right? If two particles approach each other, there exists a period during which their mutual interactions causes their motion to be deviated, right? So during which their mutual interactions causes their straight line motion to be disturbed, right? So this is what we want to study in this section. So let us see the setup here. So we expect that there is a mass m1, a point mass, which is approaching another mass m2, and let's say m2 is at rest. So here the velocity is 0, and let's say m1 is approaching with a velocity u. So we have simplified our setup here. To begin with, we assume that m1 is moving towards m2, which is at rest. Even if we don't assume this fact, then we can always say that m1 is approaching m2 with a relative velocity, right? So relative to m2, right? So without loss of generality, we have kept m2 to be at rest. So then what we expect is, so this is the situation earlier means the starting point of time, and then after, which means after collision, what we expect is that m1 and m2 are going to deviate from their, let's say, straight line motion, and let's say m1 is at an angle theta 1 and m2 is at an angle theta 2, and theta 1 plus theta 2 is theta. Okay, so that is what we have. We call this angle theta 1, that is what the incoming or the moving mass makes with the x-axis after the collision. So theta 1 is the scattering angle, and theta 2 is the so-called recoil angle, and theta, which is theta 1 plus theta 2, is the opening angle. Theta is the opening angle. Okay. So then So as I just said, let's say that m1, the mass m1 is approaching m2, right? And m2, let's say, is initially at rest, right? Okay, with initial velocity u. Okay, and then after collision, the particles retain their masses. So I'm not talking about collisions in the relativistic frame where Einstein's relation of E equal to mc square holds, where the masses get changed. So we are essentially, first of this is the primary assumption, is that the masses remains fixed in value, which means the masses of the objects don't change before and after collision. Okay, so the particles retain their masses, but emerge with velocities u1 and u2. Emerge with velocities u1 and u2, and since the system is isolated, we expect linear momentum is conserved. So isolated system, this implies that the linear momentum is conserved, right? And we see that m1u is, well, I'm just writing the momentum before collision. So we have m1u, u being the velocity of m1, and m2 is at rest. m1u is m1u1 plus m2 u2, where u1 and u2 are the respective velocities of masses m1 and m2 after collision. So the energy principle says that the collision generally is not energy preserving. So that's something that we need to be aware of. Generally, this is not energy preserving. So what I mean by that is, typically we cannot apply conservation of energy in collision theory, although conservation of momentum is always applicable, but energy conservation is not typically. But there are certain special cases where energy is also conserved, and we call those collisions as elastic collisions, right? So our total energy, which means, so what I said with this statement is that the total energy in any given point of time of the system is given by half m1 u1 square, so energy being a scalar, and plus q is equal to half m1, so u1, sorry, initial velocity is not u1 but u, so half m1 u1 square plus half m2 u2 square, right? And typically we see that q is a positive quantity. So what we have is that no, sorry, q is a negative quantity, not positive quantity. So q is a negative quantity, and q is typically the energy which is dissipated from the original system after collision, right? So if q is 0, then that is the lastic case of lastic collisions. But typically there is an energy dissipation after collision, and hence q is typically negative. So well, that is generally the case, that energy is dissipated, but sometimes energy is also gained. That is, let's say for example in nuclear reactions, that's how nuclear reactions occur. When you collide two radioactive particles, then in fact they release release energy, and that causes the explosion. So let me just generalize this concept of Q here. So what we have is Q is the energy gained. So Q is the energy gained in collision, right? And this is when Q is positive, and typically this happens when we have nuclear collisions. Example, this is typically nuclear collisions where not only energy is gained but also the masses change. So that is typically the case, but that is the type of collision we are not discussing for the time being. And in general, so this is one case, and in general Q is typically negative when energy is lost, and this is the case most of the time in non-relativistic framework. Okay, so let us begin our interesting discussion with some with some examples, and the example that I have in mind is again that of a nuclear collision. Okay, so a lot of Nobel Prizes are won in this area of nuclear collisions, and that has continuously attracted many scientists, many physicists to continue to research and find newer and newer substances. And with that, we have an example. The example says that there was a physicist who proposed the existence of a new physicist who proposed the existence of a new particle with charge +2 and mass 2, right? And the physicist has named this object as krypton, so called as krypton, right? It's not the same krypton which Superman uses in his kryptonite, but something very different. So this is the particle that the physicist named, and its name is krypton, and he calculates that this particle can be produced by the collision of two protons, right? And the equation is P plus P plus P plus being the proton plus 10 million electron volt gives you the krypton, right? So what he does is in his experiments he accelerates the protons and accelerates to some energy. Let's say the energy that is given is 16 mega electron volt, and uses them to bombard the stationary hydrogen atom, being the proton, right? So let me write this statement. So in this experiment, he accelerates the protons to an energy of 16 million electron volts and uses them to bombard stationary hydrogen atom, right? So this question is, can this scientist succeed in making this particle? So this is this question. Can this scientist succeed in making krypton? Okay. So basically, I have given the listeners an equation for making this new particle, and also I have given some energy associated with this collision. And the listeners, they have to figure out whether the energy that is given is consistent with the energy considerations of this experiment. Okay, so the setup is that we have a stationary hydrogen atom which is being bombarded with another hydrogen atom, right? So both hydrogen atoms being protons. So one of them is fixed and the other one is moving, right? So it is given that the proton with kinetic energy E, which is 16 million electron volt, collides with hydrogen atom. Okay, so it's colliding with hydrogen atom, and the initial linear momentum of the system P1 is square root 2 me, right? Well, we can directly calculate that P is m times v, but this is nothing but E by 2m, right? So P square. So P square is m square v square, but this is E by 2m because E is the kinetic energy of the proton. So E being half mv square. So that is what the formula that we are using. So the initial linear momentum of the system is 2me. From here we get the formula, right? And the final linear momentum of the particle will be, let's say, P2, right? And the energy that will be there corresponding to this momentum P2 will be E2 given by P2 square divided by 2m, right? See, so initially we have one particle which is being bombarded with the second particle which is at rest, and after collision the scenario is both particles are moving with some velocity, let's say equal velocities, but both are moving, right? So now what we see is that E2 will be P2 times 2 times 2m, not m. Why? Because initially there was only one particle of mass m which was moving, and after collision both the particles are now moving, right? So what we have is that the issue is that in this entire setup the linear momentum of the system is conserved, right? So in this entire setup we have that P1 must be equal to P2. The linear momentum is conserved, right? So if I use P1 in the formula of P2 and see what is the value of E2, I find that, so since P1 is equal to P2, I see that my new energy, the energy of each particle, right, or sorry, the energy of the system, the set of two particles, the energy of the system E2 is coming out to be the original energy E by 2, right? So the initial energy, if you look at this question, the initial energy was 10 million electron volt, and the final energy, well, hold on, we are given that the initial protons are getting accelerated at 16 million electron volts. So that is the initial energy of the accelerating proton before collision. So the final energy will be 16 by 2, which is 10 million electron volt. So which means that after collision, we should expect that 8 million electron volts of energy is released, right? But let us look at the experiment. The experiment shows that after collision, it is 10 million electron, but not 8 million electron volts which are getting released. And so this experiment is wrong, and what we can conclude is that the scientists will not be able to construct this new particle, right, based on this collision experiment that is listed in this problem, right? So this is not the 10 MeV energy released, okay, as was promised by the scientists. So it turns out that with all these minute linear momentum and energy considerations, we can do a quick calculation to the feasibility of any experiments. So this is the magic of the conservation principles, right? So the conclusion is that reaction is not possible. Reaction not possible here. Okay, so now let us start in a more in-depth study of collisions, starting with the simplest version of collisions, the so-called elastic collisions, right? So we will start our discussions based on elastic collisions, okay? So the definition is a collision between particles is elastic if the total kinetic energy of the particles is conserved. The total kinetic energy of the particle is conserved, right, in in the collision. Okay, so so that's the elastic collision. So which means that in this case specifically, when we write down the energy conservation, capital Q that we wrote, the energy dissipated, that is 0. So we can quickly write the energy conservation for elastic collisions. What we have is that half m u square m1 was the mass which is moving, is equal to half m1 u1 square plus half m2 u2 square, right? And from so now let me call this as star, and we have well, what have we got? So we also have, well, see, since these are collisions, we also have the conservation of linear momentum, right? So from the linear momentum conservation, we already have written that m1 u must be equal to m1 u1 plus m2 u2. So remember, the linear momentum conservation is a vector equation, while the energy conservation is a scalar equation, right? Scalar identity. So let me call this double star. So from star and double star, what we see is what have we got? We find that we get the following relation. So 2m1 times u1 dot with u2 comes out to be m1 minus m2 times u2 square. after doing all the calculations, which means we take the square of the double star equation on both sides and then use the first equations, we will get the following relation. And what we have is, since we have assumed that the masses of the objects, they don't change, since m1 is equal to m2, we see that the right hand side is 0, right? So we get a very vital conclusion. Well, let me just write down, hold on. So we should not jump very quickly to conclusions. Let me post process this equations a little bit more. So from this equation we get that 2 times m1 times u1, 2 times m1 times u1 times u2 times cos theta, where theta is the angle between the masses m1 and m2. So m1 and m2, the angle, the total angle, which is the scattering angle, and the recoil angle, the sum of these two. So 2m1 m2 cos theta is m1 minus m2 times u2 square, and from here I am getting that cos theta is m1 minus m2 times u2 divided by 2 m1 u1, right? Okay, so that is what we have. And so of course we expect that u1 is not 0. So u1 is well, is the initial velocity of the mass which is approaching the rest mass, otherwise we will be in trouble. And theta of course is the sum of the recoil and the scattering angle. So from here we can quickly deduce that theta must be equal to 90 degrees, because we are assuming that the masses are not changing after collision. So this is a non-relativistic framework. Typically you expect that especially in the nuclear reactions, theta will not be 90 degrees, but although most of the nuclear reactions are elastic collisions, right? But there the masses change, and hence in that case cos theta will never be 0, right? So in the non-relativistic framework we only have one solution, that is theta is 90 degrees. Okay, so let us look at one quick example. So the example is so we want to find the final energy in elastic collision. Okay, so we have a ball of mass m and energy E. Ball of mass m and energy E in elastic collision, right? In elastic collision with a second ball of mass 4m. Okay, so details are given here, and the second mass is initially at rest. It's initially at rest. See, having one mass being initially at rest, as I'm repeating, is not a specific criteria. We can always assume that the first mass is moving relative to the second mass. So this is without loss of generality. Okay, so then the problem says the balls depart in direction making an angle, an opening angle of 120 degrees with respect to each other, 120 degrees with respect to each other. And this question is, what is their final energy? final energy. Okay. So what we have is that what do we have? So well, let us use our angle equation, that is for elastic collisions. We had, the result that we had, cos theta is m1 minus m2 divided by times u2 divided by 2m1 u1, right? And what we have is that E1 by E2, remember that the velocities of the masses, so what is the initial velocity that is being given? It's given, there any initial velocity which is given? Making the balls depart, making an angle of 120. So there is no information in this problem which is given related to the velocities, and we see that all it is given is that after collision there is an angle of 120 degrees, right? So we expect that in this case we expect what do we get? So it is making an angle of 120 degrees. So using linear, I'm directly going to use the linear momentum conservation, and from there we will quickly deduce that the ratio of the two velocities after collision u1 by u2 is 3, right? Please go ahead and check the linear momentum conservation equation to see that this is indeed what we are getting, purely based on the fact that the opening angle is 120 degrees. Okay, so then what we have is that E1 by E2, in this case E1 by E2 comes out to be half mu1 square by half m4m u2 square, right? And we see that this is also equal to u1 by u2 square, and this is going to be 9 by 4 after you using all the details given here, right? So 9 by 4. Okay, so which means that the energy E1 will be 9 by 13 of the total energy after collision, and the energy imparted to the second particle will be 4 by 13 of the total energy of the system, right? And so here, so this question is, we have used the fact that the collision is elastic, right? So it's given that the collision is elastic, and the angle that the particles make is 120 degrees, right? So the point is, if the masses don't change, then the opening angle should have been 90 degrees, which means that something has happened with the masses. The masses have not remained the same after collision, such that the opening angle becomes 120 degrees. So this is typically the case of, as I said, this is typically the case of nuclear reactions, that the masses after collisions they change, right? And we expect the opening angles to be different from 90 degrees. So let us look at one more example of elastic collision. So the problem is, so in elastic collision between two electrons, what we see is one has kinetic energy E, and another is at rest, right? So it has E and the other is at rest, and the incoming electron is observed to be deflected through an angle of 30 degrees. Through an angle of 30 degrees. I think we are already out of time here for this module. So I'm just going to continue this in the next module.